Have you been in Frank's lab? We just got over $1 million settlement. That was immediately.
Good to see you. Yeah, it's been a while. Yeah, it's pretty. Things are really far right now. So I mean, getting sawdust, fertilizer. But fun time. And you hear you having a machine. But that's good.
Yeah, because they said 5 o'clock.
Yeah. They just didn't tell you which 5 o'clock.
Yeah.
Okay, well, good morning, everybody. I'd like to get started. Welcome to the PhD defense of Daniel Heaton. My name is Anthony Koppers. I'm a professor here and his main advisor, actually since 2011. So Daniel has been here for quite a while, and I can actually say when you look at his picture, he looks actually quite younger than he does today. But, time flies, right? And as a geochronologist, I know all about time. But I would just simply say, I study millions of years, billions of years. It's just like a blip on the geological time scale. So it went by actually quite fast. So few things to say about Daniel. Try always to find some, nice pictures when we go out to sea, because that's what we do. We like to go to sea, collect rocks, bring them to the lab, and do science with it. So Daniel, he's doing a PhD, right? He wants to become a researcher and want to do real research. You never know what you're going to get. And he, for some reason, got 3 projects that were technically quite challenging, to the point that there's a lot of false starts in it, and we needed to really, redo some stuff or do way more stuff to actually get to the answers. But he prevailed very nicely, and I think he got 3 really nice chapters out of it. 2 are in review. One of those is actually in revision with G-cubed. His first chapter we're still working on. He had his co-author on, I think, 3 papers by now that got published as well over the last couple of years. So he has been very productive, and I'm really happy to see him coming through with a very interesting thesis. So basically, he's rounding out the team that started we went out to, this is actually 2013 or 14, this is the second cruise he went on. But, of course, here's Daniel, he always has sunglasses on. This is me, not a guy with sunglasses. He finished, he's in the room too, and there's Susan, also sunglasses. I don't know why they're so incognito. I also don't know what we're looking at. But, we always go to sea and have fun together, and it's great to see, the entire group rounding out all our research on seamount trails and lodging in these provinces. So this is, there's many more pictures of Daniel at sea, I can tell you that, but I just picked 3 because I think, when you go out to sea, there's all these different jobs at sea that you can do. So he was our gardener. He did our bathrooms, right? He was tiling all the time. And guess what? They were doing right here. The question is, who's in the box and who are they giving, This is actually quite sciencey. There's like a little glider in there, in that box. And what you do is you actually simply take the box and chuck it into the ocean at a certain location. The box is made out of material that's not cardboard, but it actually dissolves in seawater. So the cardboard dissolves completely, disintegrates, and the glider gets freed and actually starts gliding to the oceans, going up and down, collecting data about the ocean in that location. The reason we did that there is because we were at a spot in the ocean that was quite far away from where any other boat has been gone before. So I will leave it at that, and I will give Daniel the floor. So he's just going to give us a nice presentation, And then after, say, 40 minutes, we will have some questions, and then we will break up for his committee negotiations and questions.
Yes, a negotiation. All right, thank you all for coming. Thank you, Anthony, for that nice introduction. And also thank you to my committee, Dr. Robert Duncan, Dr. David Graham, Dr. Robert Harris, and Dr. Camille Palmer. So in the background, what we have here is an image of a small piece of core from Site 1346. It's one of my study areas. And this core is kind of represent what I had to work with and some of the geologic context. This is a very nice looking core with lots of sample, but most of the time, this is not what samples look like. Usually we get maybe a nugget or so. But this is a very nice looking sample. All right. So my thesis is broken up into three distinct projects, or three main projects that have an overall theme of timescales of hotspot volcanism and their implications on tectonic and geodynamic processes. My first two projects are related to two IADP expeditions, 324 to Shotsky Rise and 330 to the Louisville Seamount Trail. My third project builds off my second project and looks into constraining plate and plume motion with Seamount Trail geometry. I had a few projects, but one of my main other projects during my PhD is I was a shipboard petrologist aboard Expedition 352 to the Izubonin Mariana Arc. And that's one of my data sets that's already been published. That data was able to get out there fairly quickly, so that's nice. All right. So to get everyone oriented with the field of study area, which is essentially almost the entirety of the Pacific Plate and the Pacific Basin. Just to orient everyone, we're located right up here in North America. There's Australia down there to the southwest. And my first project study area is that of Shotsky Rise. Shotsky Rise lies on some of the oldest portions of the oceanic crust, which is shown by this increasingly color from brown to green. We have the youngest spreading center here, the East Pacific Rise, goes all the way to the oldest oceanic crust, which is about 180 million years old. So Shotsky Rise is broken up into three large volcanic edifices, Tamu Massif, Ori Massif to the north, and then there's Sheersoft Massif to the northeast. Second project is focused on the Louisville Seamount Trail. Currently, the Louisville Seamount Trail isn't currently active, but the youngest seamount there is about 1 million years old, and it goes all the way back to about 80 million years old. And the sites that we look at here are in the northwestern portion, the oldest part of the trail. And we compare that directly to its northern analog, the Hawaiian Emperor Seamount Trail, which is an active hotspot, which you may have been seeing in the news lately, especially for the past couple of years with the eruption of Pu'o'o and all the eruptions at Kilauea. So there's a lot of activity going there. And that also all the way goes back to about 80 million years. And so one of the main things we want to look at with this project is how long does it take for these structures to be in place, and what implications does that have on the past motion of the Pacific Plate. And so two glaring things you can see on both of these trails is that they have distinct bends in them, which you may think indicate quite severe directions and change of plate motion, especially here at the Hawaiian Emperor Bend. And Louisville has a very slight bend, but so we will be focusing kind of on what these features mean for most of the talk. All right, so just kind of get oriented. So what's going on beneath the Earth's lithosphere that could be generating these large volcanic edifices and seamounts in large igneous provinces. And so here is just an interpretation of the upper, lower mantle, which are above the core of the Earth. And what I want you to focus on here is the red, which has recently been described as large LSVPs, which is large low shear wave provinces. And what these areas indicate are areas of high temperature and slow shear wave velocity. And so this means it's a little bit hotter, but then there's areas with blue, which have higher shear wave velocity, which they interpret as being slightly colder. And here this interpretation is is that this is actually subducting oceanic crust beneath the lithosphere. In this case, this is right around the top of North America. And how they interpret these large igneous provinces, and they've been correlating the location of modern-day hotspot locations and large igneous provinces to the boundaries of these massive structures that are around the core mantle boundary. And these produce mantle plumes, which impinge on the bottom half of the bottom of the lithosphere and generate large igneous provinces, which are these large, massive volcanic edifices. And then there's mantle plume tails, which are being associated with the edges of these zones, and they produce seamount trails. And so we use these seamount trails that are being produced by these plume tails. So as those erupt, they are erupted on a moving tectonic plate. The tectonic plate moves away, carries them away, and new ones are generated. And we can use those generations of seamounts to test the motion of the Pacific plate. All right, so get into the first project of Shotzi Rise. So Tamu Massif represents a single lip-forming event, and the age progression is closely related to the migrating ancient Pacific Izanagi and Farallon triple junction. And one of our main conclusions is that Tamu and Ori Massif are closely linked to the age of the oceanic crust. So a triple junction is where three tectonic plates meet. And in this case, this is a ridge triple junction. So there's three mid-ocean ridge spreading centers. And so that's not a very stable scenario. And it's interesting that it's closely associated with the emplacement of Shotzi Rise. So we can see that Shotzi Rise was previously studied using the magnetic lineations on the seafloor, which are measured by the devices Anthony mentioned earlier. When they throw these devices off the back of ships, they measure the magnetic signal inside the oceanic crust, and they can build these like little barcode maps and determine the age of the oceanic crust, which is pretty interesting. And so I just want to quickly show here is that with these magnetic lineations, they were only able to, by kind of associate the triple junction with the formations of Tamu Massif, Ori Rise, and Shearsov. And what we hope to do is see how close the oceanic crust and these massifs are actually linked together. Right. So here is a topographic, or a bathymetric map of Shotzi Rise. So if you get your oriented, north is actually to the top right of the diagram. So Tamu Massif is here in the left, Ori Massif in the center, and Shearsov Massif on the right. And our field of study is these IDP expedition holes. We also dated an older site from ODP Leg 198, 1213B, which is in the southern portion of Tamu Massif. The new cores are at 1347A and then 1350A for Ori. We weren't able to get any good age data for 1349, and then 1346 for Shearsov Massif. One thing I want to again point out is the relationship between the magnetic lineations, which are interpreted, which represent the age of the oceanic crust, and their orientations around these massifs. And these actually penetrate into the massifs, which is kind of an interesting, which is not a common feature for some volcanic seamounts on the ocean floor. Normally, the crust is old, you emplace a new seamount, all these signals are covered up and you don't see them. But it's interesting that these are actually penetrating into these very large structures, and so that makes us think that it is indeed closely related to the formation of the oceanic crust. All right, I won't go into the stratigraphy too much, but this is kind of like all the age data that we analyzed with a number of analyses done under each stratigraphic column. Each of these sites had a really thick coverage of sediments, about 160 meters for 1347A, but ODP site 1213B had about 400 meters of sediment coverage. And there's about 150 meters of igneous basement, which are comprised of lava flows, or massive basalts, and volcanic plastics, and maybe some pillow lavas with interspersed sediments. And one thing that's kind of interesting is that, especially for Ori Massif, over about 150 meters, we have the same age through that much of the material, which is kind of interesting, and it's closely linked to the age of the oceanic crust. All right, so before I get in, I'm not going to show all my age data because we'd be here all day, but I'm going to show or describe kind of the concept behind argon geochronology, which is our main data collection method. So the argon geochronology is an accumulation clock. It is based on the principle of the buildup of argon-40 from the radioactive decay of potassium-40. And so what we hope for is that when a rock erupts on the ocean surface or anywhere in the world, that it equilibrates with the atmosphere and it inherits the 40 argon-36 argon composition of the atmosphere, which is 295.5. That's our beginning isotopic ratio, and then with the buildup of this over time, we can then calculate the argon-40 signal. But it's usually not that easy. Samples they're in the ocean for about 140 million years. They have lots of alteration, and we kind of have to deal with that. So our sample processing method is we choose a rock sample, we crush it into very small pieces, maybe 200 to 300 microns. We leach it with like hydrochloric acid, nitric acid, possibly hydrofluoric acid, and we pick them very carefully under a binocular microscope. And then this is where part of the magic happens, where we stick it in the nuclear reactor here on campus, and we actually convert potassium-39 to argon-39 to be able to stick it in this age equation over here. Then we load the samples into these nice little trays here, where we incrementally heat them and analyze the resulting gas in a mass spectrometer, and then we do the fun calculations. All right, so here's just one example from this study. So most of the samples that we collected were pelagic clays. Most of the ground masses were a bit too altered. And here on the right is an inverse isochron diagram, which plots argon-39 40 versus 36 over argon-40. And what this line represents is the atmospheric intercept line. And what we would hope for is that all of our data points would fall directly on this line, and we'd go, great, we have a great age. But with this study, most of the pelagic clays samples we analyzed were highly radiogenic with no really good isochron. So we had to rely on plateau age diagrams, which is over here. And this represents the age of each step, incremental heating step in the experiment. So below is the cumulative argon-39 released over the experiment versus the age. And so you can think of this diagram from left to right, or sorry, from low temperature to high temperature. So those low temperature ones, or low temperature steps, are usually a bit discordant, not the right age, but as we get to the moderate and high temperatures, we hope that they even out and that we assume the initial composition of 295.5, and we can get, hopefully, valid ages, which these two are actually fairly good, and we get agreement between two ages. These are also difficult because they have an extremely low potassium-calcium ratio, or low potassium in general, like orders of magnitude, like maybe 2 orders of magnitude less than other basalts or ground mass samples. So that makes it even more difficult and troublesome, because any little blips, such as here in the higher temperatures, can mess up the experiment and contaminate it. All right, so again, we want to take another look at the crystal structure of Tanui Massif and kind of how that relates to the location of our drill sites. So here we have two seismic surveys that cut across two directions of Tanui Massif. So here, A to B, or west to east, or on here, it's top to bottom. And then another seismic line from the southwest to the northeast, which is from here all the way to here. And what I have over here superimposed on these seismic lines are the locations of our sites of interest, 1347A, which is here just near the top of the Tanui Massif. And then we have site 1213B, which is a little bit further south from the top of it. And well, we can see some interesting features like Toronto Ridge. We also dated this from a dredging cruise back in the early 1990s. We reanalyzed some samples and got this age that's about 20 million years younger than our oldest age. We think this is not related to the initial formation of Tamu Massif. And that age has actually already been published and presented in a different paper. And so what we can see here, there's not a lot of cross or magnetic lineations in this cross view because it's going kind of along strike of the magnetic lineations. But if we look at the very long seismic survey, we can kind of see the age progression of the magnetic lineations. And so we can go from the top where they intersect here. So our core site is like roughly right here in the center. And we can compare it to the age of the oceanic crust, the interpreted age of the oceanic crust, which is 148.4 million years, and the age of our site is 148. So we can see that they are very closely linked, and it wouldn't be M19, which is 146 million years old. So what that allows us to do is give it essentially an initial age of the construction of Tamu Massif, where we can give it a lower age. And what it allows us to do is calculate emplacement rates, which we really can't do for a lot of large igneous provinces. So the eruption rate that we calculated for Tamu Massif, we're going to go back real quick because I forgot. So right here is the cap of Tamu Massif, and there's a volume associated with that. But what I don't show here is its associated deep crustal root, which extends to about 7 kilometers beneath the ocean floor surface. So there's a whole other part of Tamu Massif that we can account for volumetrically. So without that crustal root, we can calculate an eruption rate between 1.8 and 4 cubic kilometers per year. And with the crustal root, it can go up to 3.1 to 7.7 cubic kilometers per year. And you're kind of wondering, well, how does that kind of relate? What does that mean? And the only way I can really kind of explain that is, or illustrate that is, comparing it to the global melt production rate at mid-ocean ridges. So entire globally, of all the mid-ocean ridges, the global production rate is about 20 cubic kilometers per year for modern day eruption rates. Kind of back in the time when this Tamu was going on, it maybe was up to more like 60 cubic kilometers per year. So it's quite a bit, and this agrees closely with a continental large igneous province, the Siberian Traps, which was between 3.7 and 6.1 cubic kilometers per year. Hawaii, talked about a little bit earlier, the island of Hawaii, that erupts at around 0.14 cubic kilometers per year. So it's an order of magnitude more, and they're actually probably erupting in the same time period. So Hawaii was probably formed in 1 million to 1.5 million years. Tamu Massif was probably formed in about 1 million years, but generating an order of magnitude more magma material. And so this is really the first time a oceanic plateau on the ocean basin we were able to constrain the eruption rate, which is cool because normally we don't have access to the bottom of these large igneous provinces. We just can't access them in any way. So just some kind of benefits of having the age of these massifs so closely linked to the age of the oceanic crust. We can actually assign them to the age of, we can assign them the age of the oceanic crust. So previously this was done with the initial ages at Tamu Massif of Mahoney et al. 2005, where they assigned the age of Tamu Massif, which was 144 million years, to the chron of M18. But now we can use our ages of Tamu Massif and Ori Massif to kind of add more data points. And currently, so this is the time scale, the geomagnetic polarity time scale between 125 and 180 million years. And that only has currently like 5 radiometric dates calibrating that time period. And 2 of them are actually only on the oceanic crust themselves, which are up here and analyzed by Anthony Coppers. So we're proposing that we can add these 2 data points to help calibrate that time scale. And it doesn't change it a whole lot, but it does imply slightly slower spreading rates between 125 and 150 million years, and slightly faster spreading rates between 150 and 180 million years. Okay, so now we're going on to the second project for the Louisville Seamount Trail. And some kind of made the takeaways associated with this is that the Hawaiian Emperor Bend and the 169 Bend in Louisville are asynchronous by about 3.7 million years. The Louisville lava flows analyzed are successfully corrected for the presence of trapped argon, and previously assigned seamount ages in absolute plate motion modeling misrepresent the inception ages of hotspot seamounts. All right. So first, I kind of want to get out of the way, kind of, I guess you can call them technical issues with this data set, because it's a very large data set, and we had a lot of interesting age results that we kind of had to decipher. And so what I want to kind of point out here is start off with the thin sections here. So what we're finding is the excess argon is present in olivine crystals. So here's a thin section of a common Louisville basalt. We have a nice kind of apheric grand mass with some very large olivine crystals interspersed with them. And when we pick samples, we avoid these. We do not want to pick these because they do have mantle gases associated with them trapped inside. They don't always degas completely. And this sample itself, while we avoid these, we still had an elevated signature for argon 40 to argon 36. So initially I explained that we almost always rely on the atmospheric composition to be 295.5 because that's our beginning composition. But if the sample doesn't degas, then we have to try to figure out the initial composition. We do that through the inverse isochron. And so what's shown here in green are the inverse isochron intercepts of the samples at this site, plotted against, in purple, the noble gas analyses measured by Hanyu et al. 2014 on the same site. Not necessarily the exact same samples, but they're very close. And so we avoid the olivines, but we're still getting elevated. We're still getting elevated argon 36 values. In a thin section where there's no obvious olivine phenocrysts, we are still getting slightly elevated, in this one, very slightly elevated ratios. But if we did some electron microprobe analyses, so we have an electron backscatter image here, and we have a combined potassium, iron, magnesium, and aluminum element map here. And what we are able to kind of find is that there are very small microcrysts of olivine in these samples. So this grain size is about 200 microns. So they're very small, and this is kind of what we think is the culprit for our excess argon component in our samples. And it's very interesting how well they mimic the actual intensities of the independent analyses done by Hanyu et al. All right, so this is kind of what it looks like in practice. So up here is the incremental step heating experiment for a sample that has an excess argon component. So what this normally looks like is that we have high early low temperature parent ages, and it slowly slopes down, and we're able to maybe get a very small plateau with about 37% total gas with a poor MSWD and statistics of 2.69. We would like it to be around 1. So that doesn't work. But if we go look at the inverse isochron, we can see that there is a nice isochron that points to initial composition of 578. So we can stick that back into the plateau age and kind of change the initial composition, and we get a much better, wider age plateau, where we get a plateau width of 63%, and we have better statistics of 1.64 MSWD. But more importantly is the change in age, where before it was 63.8 and now it's 63.2. That's a 600,000 year age difference, and it's out of error of each other, and that has implications for the stratigraphy of the seamounts. All right, so from this point on, we're going to be mostly focusing on the inception age of seamounts. We'll talk about this from the rest of this project and into the next project. So first, I want you guys to think about what are we actually collecting when we're sampling these seamounts. So here on the left is a nice figure made by Susan Schnurr. Thank you, Susan, where she just had she made some profiles of some seamounts and their associated drill hole core depths. And for most of these, we are just barely scratching the surface when we're drilling into these edifices. You may think we're getting down to the center of Detroit Seamount, but this is mostly sediment. Most of this is actually sediment, but there's only a little tiny thing there. But so mostly we're just getting the very top of it. And through dredging, what Anthony talked about earlier, where at that point we're taking a big metal bucket and raking it across the top of these seamounts, and we're going to get whatever we get. And so to kind of think about how these seamounts form, we can look at a growth model of Hawaiian Island. This is some modeling done by Littman et al. In 2013. And he finds that the entire shield building stage of Hawaii happened over the course of 500,000 to 1 million years. And it happened in distinct pulses. So big kind of like manifestations of that is Mauna Kea and Mauna Loa. And then right now, so this was like the shield stage portion of Hawaii, and right now we're probably kind of into the post-shield stage with the eruption of Kilauea and Luihi with Kilauea and Luihi. And so now you kind of have to think about this as an island, and once the island of Hawaii moves away from the hotspot trail and starts to subside, and then starts to erode and becomes a guyot, it's going to chop off a lot of this material, and kind of the question is, what are we left with? And are we sampling in our core of these seamounts, or are we getting maybe some rejuvenated stage or post-shield stage lavas? All right, so what we found at Louisville, I'm going to go over this real quickly. Here again is all the age data for Louisville. What we can see is that each of the Louisville seamounts, there's very little seamount cover, maybe about 50 meters, which is a mix of pelagic ooze and conglomerates. But the igneous basement was mostly comprised of volcanic clastic rocks, hyaloclastites, and maybe some lava flow packages and pillow lavas. And the age variation in the igneous basement for most of these sites was only about maybe 1 million years. If we're lucky, maybe 2 million years. So even for Rigel Guyot, where we collected about 500 meters of igneous basement, there's essentially no age variation through that core. So, but where the real age variation came actually was in the sediment cover, where we got a collection, a myriad of different types of rock types that were probably deposited from across the entire structure, where we were able to get a larger sampling. All right, so now we're going to think about the seamount inception age in terms of the duration of seamount volcanism that's been recorded so far. And so, as I talked about earlier, there's 3 distinct volcanic stages. The shield stage, which comprises 80 to 95% of the volume, post-shield stage, which is less than 10% of the volume, and rejuvenated stage, which is less than 1%. But what's interesting is that while these 2 stages comprise of most of it, there's not a lot of data associated with it compared to the amount of data that we have for the rejuvenated stage, which is a very small portion of it. But what I want to point out here, so for each seamount that I took from Hawaii, I took the oldest age of it, and I subtracted all the other ages from it. So this is the oldest age, and this is the youngest age, just to get an idea for how long, what age range coverage we have. So what's interesting here is that what I want to point out is the difference between shield and post-shield lavas and their age distribution. It seems Kauai is a fairly well-studied Hawaiian island. There's been a lot of analyses, a lot of field work done, and there seems to be some discrepancy in the age and characterization of these rocks, and whether or not they're shield or post-shield lavas. So it's fairly difficult to discern between the two in hand sample and even through geochemical analyses. The rejuvenated stage has very distinct characteristics, and they are able to kind of separate the two. If we look at all the other Hawaiian Emperor seamounts, we can see that the shield and post-shield stage lavas are kind of intermixed with each other, and they were able to maybe correctly discern between the two. Even for the older ones, the shield stage lavas even spanned up to 5 million years, but this also could be due to alteration. So some of this variation could be due to alteration, but the rejuvenated stage lavas were able to be separated from it. But with Louisville, we don't really have the ability to look at shield stage, post-shield stage, and rejuvenated stage lavas because it's a fairly homogeneous, all the samples are fairly homogeneous. We can't really do that characterization. So that's why I kind of focused on looking at the age differences between the samples to determine the lifespan of it. So with Louisville, we can see through all the dredged and cored samples shown here that there's mostly an age variation of 2 million years between the seamounts, with some ones that do have a slightly larger age range. And this is actually very similar to the distribution in Hawaii with their core and dredge samples. They're about 2 million years, maybe a little bit longer. And so a lot of seamounts, we don't have a good age coverage, so that leads us to believe that we don't have a really high confidence in what the inception age of the seamount is. So here we developed a little index called the Inception Age Confidence Index, or AXI, and this is meant to go through each seamount in the Hawaii and Louisville seamount trails and assign some type of ranking on how well we think we know the inception age. And I don't think I said this, but inception age is important for conducting plate motion models and whatnot, and having the exact time when that seamount was beneath the mantle plume at a given time. So an example of a high score at like Hadar Gate, we have, this has been cored and dredged. It has about 8 ages, and it has a high rating because of the number of samples and the time span. It has about 6 million years of history that's been recorded, and so we can be pretty confident that the oldest age is really close to the inception age of the seamount. A moderate example would be Cocoa South, which has also been cored and dredged. That has 12 ages, but it is a moderate ranking because it only has an age range of about 2.5 million years. We don't know for sure, we're not entirely confident that maybe this isn't the entirety of the rejuvenated stage volcanism. And a lower ranking would be only maybe 2 ages with about a 3 or 4 million year age range. Those are just some examples. So we take this age data, or we take this kind of ranking system, and then we apply it to every seamount in both these seamount trails, and we then fit an age spline through these points. So highs are blue, moderates are this other blue, and then lows are this green. And the white symbols are alteration ages, and this other color is there's none. And so we fit age progressions through these, or age spline, and then now we can compare the two age progressions to each other. And what I want you to focus on here is just this red line. So we just compared the opening angle from the hotspot location to all the way back to 80 million years and compared the two. And we can see here, Louisville and Hawaii are essentially mimicking, mostly right on pace with each other. It gets a little wobbly around here, but then at around 45 million years, the two paths completely diverge and they do not match up at all. And of course, this is happening right around the Hawaiian beginning, or the end of the Hawaiian Emperor Bend at about 47 million years. And so what's interesting here is that we can project like the bend at Louisville at 169 degrees west and project it onto that location in Hawaii. And it turns out those two bends, the bends in Hawaii and the bends in Louisville, aren't necessarily happening at the same time. There's about a 3 to 4 million year age difference between the two, which are located here. So you would think that, oh, since there's these two very distinct bends, they are probably happening, right on top of each other, but they are not. They appear to be some way desync, and this could be because, possibly because of changes in plate motion, plume motion over time. And what we want to try to constrain, especially in the next project, is how those hotspots are moving over time. All right, so now we're going to the third project pretty quickly. A lot of this is kind of like preliminary results. We'll try to get through this. So in this figure, this is just the Louisville Seamount Trail with all of its age data. So this is represented as angular distance from the hotspot versus the age. And kind of what I want to point out here is the current moving hotspot and fixed hotspot plate motion models. And all of them overrepresent the age progression of the Louisville Seamount Trail. They appear to work okay with the older ages for seamounts. They don't disagree with it too much. But with the new ages, we can see a definite discrepancy between that and the models. And so with this project, what we want to do is try to build a plate motion model that resolves the age progression for both seamount trails. And to do this, I built a kind of like a bootstrap method to be able to find the correct Euler pole and Euler rotations to describe both seamount trails. So just quickly, what an Euler pole is, it describes the rotation of points on a sphere. So what we want is an Euler pole that will fit through the seamounts of both Louisville and Hawaii and describe the motion of both with using a single stage. And a stage pole could be from from present day to about 5 million years ago. And this diagram, just quickly, this kind of describes our algorithm a little bit. We take the fixed hotspot locations, we rotate them back over a course of 5 million years, and we vary we do a brute force search for the stage pole that resolves both seamount trails. We vary the opening angle of that rotation, and we do that all the way back to 80 million years. And we just run thousands of models, and then in the end, we can then filter those models and see which ones best fit the seamount trails. So our first initial test we tested the fixed hotspot hypothesis, and we could only rotate this. We could not resolve both trails back to 80 million years. We could only resolve it back to about 45 million years. And so now the second part of this test is to then test the moving hotspot hypothesis, where we then introduce plume motion, so that now it's no longer fixed, the plume is moving over time. And to do that, we created some very simple linear motions of hotspot motion based on the known or possibly known hotspot motions over time. So here on this figure is paleolatitude measurements, which as paleolatitude, it's what they think, or it's measured the latitude that the rock worked at the time. So this is distance from hotspot. So Hawaii, they measured, it had up to maybe around 10 degrees of motion back at around 80 million years, had maybe up around 8 degrees of motion around 65. And Louisville has maybe up to around 7 degrees of motion, but each of these have very large error bars. And so what we want to do is create an individual check on these hotspot motions. So instead of relying on, well, maybe we should just move them exactly this much and see what we get, what we'll do is that we'll just use the geometry and age progression of the seamount trails to see if we can solve for these, if we can find this amount of motion if we start varying seamount motion paths by themselves. And so I tested thousands and thousands of combinations of hotspot trail motions, hotspot path motions in various configurations, and these are the results of that. So first, how we calculate model statistics is that we calculate the orthogonal distance from the seamount trail to the model, and then also the seamount from the seamount age to the age of the model, and we add those up over the course of the entire run. And then the ones with the lowest sum of fit we consider to be the best fit. And so here are the preliminary results. And so first we're just going to start on this side of the diagram. So I broke these up. I broke all the results up into 3 sections. We have the Hawaii and Louisville lowest sum of fit models. So this is a balanced approach to filtering the results. Then we have a Hawaii fit priority, which is we take the best models from that fit Hawaii, and we didn't care about Louisville. Then we have the Louisville fit priority, which we cared about the age progression of Louisville, but didn't care about Hawaii. And what we found is that the balanced approach and the Hawaii fit approach, they don't really fit the age progression between 45 and 80 million years, the age progression of Louisville. They look like the older plate motion models. But the Louisville fit priority models, they fit both trails fairly well, at least the preliminary results do, and which is actually pretty interesting. So we can look at what the plume motions look like, which are shown here for Hawaii and here for Louisville. And what we can see is that on average, Hawaii has shown a motion of about 4 degrees of latitudinal motion, with a varied amount of longitudinal motion. Louisville showed very little latitudinal motion, with most of the good results having no motion at all, and also varied longitudinal motion, so we can't really constrain those. And so that is it for chapter 3. And so that's about it for the results. So all these, as you can see, my main focus on these was just figuring out when these very large seamount structures and large provinces were formed and how long they take. And with that, we can figure out some pretty interesting stuff with maybe how plate mason works and maybe even how the mantle operates over time. All right, so I'd like to give some acknowledgements because I'm like over time now, but that's okay. So first, I'd like to thank my advisor, Anthony Coppers. He's been extremely patient with me through this entire period. I really appreciate it a lot. I'd also like to thank my committee members, Bob Duncan, Dave Graham, Herbert Harris, and thank you again, Camille, for stepping in essentially at the last moment. I'd really like to thank Dan Biggins. You've been great. You've been very helpful for me harassing you all the time. I really appreciate it. Definitely made this a whole lot easier. I'd like to thank also other lab. When I first arrived, Julie Clapp and Trevor Smith were actually starting to work on my samples when I first arrived. So I thank them because I'm now able to place blame on them when something was wrong down the line. So thank you, Julie and Trevor. My former advisor, Aaron Petruska. Thank you, Aaron, for listening to me and talking with me anytime I needed to. And my friends, most importantly, Susan. Susan, it's been great working with you. I love you a lot. And then April and Mike Rucker, Abby J. Hunt, Christopher and Matthew, Andrea and Kevin. You guys are all great. I like the Viper group. I've been absent for the past 3 years, but let's not talk about that. I enjoy and appreciate that. I have to thank my family, my parents. Thank you so much. The Browns, the Crockies, and the Kahn family, and most importantly, Julie. Fauna. This is what Fauna looked like most of the time when I was working. She was just wondering what I was doing and why I wasn't feeding her. And that's it. Questions?
Yeah, questions?
Oh, that's actually not. Oh, that clock's wrong.
Okay.
Okay.
How does your Hawaii plume motion compare to Tarduno's work, my work, and some of Wessel's work? Is it similar? Seems to be.
Yes, it is. It is very similar to like Tarduno's 2016 or 2017 paper. Can't remember, but I think he suggests there's like 5 to 7 degrees of plume motion between the time period of 50 million years to 60 million years. With your work, it is. With right now, I can't do it with the resolution that you conducted your work, but one of the next steps of this project is to kind of maybe specify when the plume motion happens and see if we can kind of look at your work and see if we can maybe figure out if that's when create models that account for the differences in trail geometry. Yeah.
Yeah, this is great because there's still a lot of people arguing that the motion Hawaii is not moving and it's all just change in dipole moments and everything. So
Yeah.
I think this is wonderful to say
Yeah.
that's not right.
Any questions?
Can you explain why there's a rejuvenation stage?
That's a great question. I don't know. So probably should have. So I did. Maybe we'll just go back to here. been a while since I thought about it. There it is. Okay, so generally when a seamount erupts, it's because there's like an initial there's initial burst over maybe 1 million years that implants most of the shield stage volcanism, but seamounts are kind of thought to be formed in pulses. So that first initial pulse, most of the volume is erupted. But as the seamount moves away, there's still some remnant kind of like pathway. I think like pathways that still have access to the seamount, and so you just get these usually they're distinct compositions of lavas that kind of get siphoned in, and they erupt over just a very long period of time. They kind of sputter out because I think they're still somewhat connected to the plume underlying the or kind of they still have connections to the plume as it moves away. So usually the rejuvenated stage doesn't happen until it's a million year or two. It's moved about 1 million or 2 years away from the hotspot, the current hotspot. So it's just still some remnant volcanism, and I can't exactly remember why they think that happens. I haven't looked at that in a while.
So it doesn't link up to this, so you have that main plume and then you have this little wispy thing coming off the edge?
Yeah, it's like, so if this volcano was going through rejuvenated stage volcanism, it would be, like right now I think Kauai still has some stuff, so it's a bit of ways away from the current hotspot, but it's still influenced by that overall region, because these plume tails are actually covering very large areas. It's like 100 kilometers. So it's still in a very hot region, which I kind of forget about sometimes. You think about this in these graphs, you're like, oh, it's just a single data point. So it's right there, but it's a whole region that's being affected by that. And they kind of still are affected by the hot spot at that point. Yeah, that's what I'm going to say. Any questions? Super exciting.
Okay, no. You must have done an excellent job.
Oh, yeah, of course.
Made them all quiet. Well, let's thank Daniel one more time. And